Please join me in welcoming Dr. Stephen Benner.
Thank you very much. Is this on? Is this on now? Okay, so we can see whether I'm smart enough to turn it. It's on. Oh, excellent. It's amazing to see so many of you. The Fox News Channel has said that there's a 60-mile-an-hour weather alert for Long Beach as the storm comes in off of the Pacific. So I just came down from Ventura, where we're coming from a large meeting on the origin of life, and with everybody throwing ashtrays at each other because we're having an argument about whether metabolism first or genetics first was the correct way of looking at the origin of life. I'm beginning to lose my voice, and so I'm going to try to do the best I can here to introduce a subject to you that's interesting to many people, but it has an enormous amount of technical details which makes it difficult to actually to grasp unless you're in the field specifically. I'm going to try to do a triangulation, not knowing really actually where you folks are coming from. Who here, just as a matter of curiosity, calls themselves a scientist? Raise their hand. And a humanist? Raise their hand. A physician? A lawyer? Oh, you want to know. I'm not sure how much you're into science fiction. This is actually a Robert Heinlein book, which was adapted to a movie with Donald Sutherland and Eric Tall and other people, where Tall played a guy named Sam Niddens, who is going to go and come across these aliens, which have the habit of fixing themselves to humans in their backs and then controlling their brains by putting processes in their brains. I don't know who's seen this movie. I mean, it was not a very pleasant movie, but there's an exchange between these characters where Mary Sefton, who is Sefton here, is brought in, and Niven says, what do you exactly do for medicine? The answer is, well, my specialty is exobiology. Exobiology is the study of what alien forms might be like. Nivens, you actually make a living at that. Seems like it would be a lot of guesswork. Well, we had a little joke in school that ours is the only science that didn't have a subject matter. In a sense, that's what a lot of us are working on in terms of origins of life, because you're talking about an event that's occurring billions of years ago. We have really no direct evidence. You want to talk about alien life, you know you have no real approach to seeing it until someone comes down and shoots us with a ray gun. And so my 15-year-old kid who's just gotten through middle school science, when he has been taught the scientific method, we're at something of a loss to apply the scientific method to these kinds of big questions, we like to call them. I mean, everybody can, apply the scientific method, which is to ask a question and do background research, construct a hypothesis, test with an experiment, analyze results, draw conclusions. The hypothesis is true or the hypothesis is false, or partially true, report the results, and think and try again. Now, if you decide your question is how did life originate or what does alien life look like, you're going to have a hard time applying this. And actually, all the parents in his school who are actually practicing scientists go back with horror to our laboratories and say, well, when is the last time we actually did this? It's not actually what we do. And in fact, one of the things that a good philosopher or scientist will tell you is there really is no neutral observation of the world. You really don't actually. And I wish that we could construct experiments that would allow us to distinguish cleanly between whether a hypothesis is true or false. And the problem only gets worse the bigger the question gets. Now, science without a subject matter is not a big problem, right? Because scientists all the time study questions about, well, they study things that they don't observe. So, for example, Galileo's, there's Galileo in case you didn't recognize the chap, his big question was, does the Earth go around the Sun or does the Sun go around the Earth? Now, the logic, in fact, this is a perfectly good Aristotelian syllogism, was that, if the Earth went around the Sun, then we would feel its motion. We don't feel its motion, therefore the Earth does not go around the Sun. And that's actually quite a solid argument, frankly, for anybody, even in the modern world, let alone in the late Middle Ages. So what Galileo actually did was roll balls down inclined planes. This is actually out of the museum. They actually have some of those devices, and what he's doing is he called this diluted gravity, and he would measure the rate at which the ball accelerated by putting bells down that inclined plane. So as the ball rolled by, it would ring the bell, because the human ear is very good at seeing equal spacing of sounds in time, and so that was the way he was able to show that the ball accelerated at a a squared law as it rolled down the ball. Now, there is a direct connection between a rolling ball at an inclined plane and celestial mechanics. Right? It's partly because the idea is that the fact that you're moving around the sun, but if the air is moving around the sun with you, you actually don't feel the breeze because you're moving with the air. And there's a direct relationship between that statement, the statement that a heavier ball and a lighter ball fall at the same rate when you roll them down an inclined plane or when you drop them apocryphally off the Leaning Tower of Pisa. So it requires some intelligence to make that connection, but the real difficulty is that it requires especially a lot of effort if you are trying to persuade somebody of that connection where that person doesn't want to be persuaded. And that's, of course, the problem that got Galileo into so much trouble. So science without subject matter is not the problem. Trying to persuade people who don't want to be persuaded is the problem. And, of course, keep in mind that as a scientist, you're involved in the theory as yourself. It's not so much that you don't want to be persuaded, it's that you do want to be persuaded. And, in fact, say your I'm not sure if anybody is a fan of Calvin and Hobbes, but Calvin has the episode of waking up and realizing that his mother is serving his breakfast as just a finger puppet being put into his secret house by an alien who is feeding him breakfast and studying his behavior. And when he realizes that's the case, the alien says to the other alien, well, there goes our grant, Wayne. So the bottom line is that we, as scientists, of course, want to believe, and of course the people who are on the other side don't. Now, what's quite clear is that whatever science is, and that's what the discussion is this evening, is people certainly want to be associated with that word. I'm not sure. There are fields of science that you recognize. There's chemistry, there's physics, there's biology, there's geology, and those are sciences. But there are, of course, other fields of science which have the word science in them. So there's political science, computer science, and social sciences. And, of course, they're associated with a certain type of thing. Now, for those of you who can't see this cartoon, you're walking down the street, you see the time and the temperature and the quality of light. Now, you know that social science is not a science because chemists do not make fun of the fact that they measured the weight of an atom to a few percent or biology. Right? So this is computer science, or famous computer science. Nicholas Beers, who is actually maybe known to you, he's a Turing Medal winner, and he's also the man who invented Pascal, among other things, for the people who program. Pointed out that if it has the word science in its name, then it's not a science. But of course, lots of people want to have that word with it. And so, there's creation science, there's Christian science, there's Scientology. Even Tom Cruise is called scientist. And so what is it, you might ask, is it about the scientific method? It was certainly not what we had on an earlier slide that gives science the power, and of course, the people who want to be associated with that power, the desire to have. Now, who here is a philosopher? Raise their hand. Okay, not enough of you to throw me out bodily now. So, you can turn to philosophers and you say, can they help? And of course, they certainly do try. And I think this is a long tradition where, I'm critical of most practicing scientists because they don't actually know enough of this tradition. I'll just put a few things on the board, especially for the students here. There's Immanuel Kant, affectionately known as I Kant by his people, trying to talk about, and this is critique of pure reason types of stuff, as he's trying to understand what it is that allows us to say that we believe what we believe. And so, he talks about analytical statements, which are statements that we can see are true without needing to make an observation. So, for example, all bachelors are unmarried. There are then synthetic statements. Those that require observation, so all emeralds are green. And so that's an early attempt, not so early, this goes all the way back to Aristotle and beyond. So our effort as humankind to interact with the world, to understand what it is we think we should be believing and why, is a lot older than that. But then along comes somebody, this gentleman, this man is actually Willard Van Orman Quine, who's actually a philosopher at Harvard, and he basically sits out, and for the students, I do recommend, Quine is such a good writer, he's actually somebody you should go back and actually read the primary text of, not read somebody else writing about it. But what he basically does is goes back and makes the point at great length. There actually is no real distinction between these types of statements if you are going to get serious about it. Now, I actually had got to know Quine quite well, and he's like many philosophers, he's extremely annoying. And that's because he's extremely precise with language. So I say, look, I mean, it's obvious that that statement does not require, right, observation. It's embedded in the definition. So he said, well, where did you get the definition? Well, I looked up in the dictionary, so that's an observation. That's the essence of the argument. We won't go further. You know, most scientists think that scientific propositions can be distinguished from non-scientific propositions. And this is Karl Popper, mid-20th century philosopher, who basically made the distinction or a demarcation saying that a scientific proposition can be falsified, whereas a non-scientific proposition cannot. And so the statement, for example, all animals are green, which would be called a synthetic statement from the previous slide, you could imagine observing an emerald, so object X, which you could say is an emerald, and you can imagine seeing that it's not green. That's the falsified observation. Therefore, the observance of X could falsify the proposition that all animals are green. Therefore, the proposition is a scientific one because it could be falsified. Now, I've already given you a heads-up warning as to sort of the cynicism here, right? If you were the guy who came up with the theory that all animals are green, and if your grant application or tenure decision is based on that, right, you would have a problem accepting the observation of an X that's not green as a falsification of your theory. In fact, what human beings naturally do when a theory contradicts data is that they discard the data to save the theory. And that's what all scientific happening as well. So here comes Quine again. He doesn't like Popper either because there's an emerald. I assure you that's an emerald. But it's being viewed, of course, under long-wave ultraviolet light, and you'll notice it's not green. So this is a problem with philosophers. They treat language very precisely. You say, well, okay, that's not what I meant. What I really meant was that all animals are green when observed under white light. Okay, so we'll make that now as my scientific law. And what Quine has basically pointed out, that's an ad hoc hypothesis in a sense. You're modifying the theory after the fact, just try to bail out the theory from an observation that is contradicting it. And Quine's point, you can do this indefinitely, because now you have to say all animals are green when observed under white light by someone who does not have red-green color blindness. Right? And so this is, of course, a problem because modifying an ad hoc hypothesis is entirely reasonable. You most certainly should not throw out the theory when you observe an emerald under non-regular white light. There's no reason to throw out the theory at that point. But, of course, it looks a lot when you do that rationally. It looks a lot like what you do when you don't want to discard the theory, even though you have good reasons to discard it. And we'll come back to that in just a moment. So even definitions get to be a problem when you talk to philosophers. Okay, so for example, we want to look for extraterrestrial life, or we want to know what the origin of life is. So at some point, you have to ask yourself the question: what is life? Now, I don't know how many of you have ever had a discussion in a bar or a parlor game on this particular thing. I just got a collage of things. No one knows what life is, right? It's hard to actually capture the definitions of life. But then again, if you talk to a philosopher like Carol Cleland, who's written a wonderful article on defining life with Chris Chiba, you'll walk out of the bar at the end of the hour convinced you can't even define water. And so the philosophers basically will then educate and define definition. So the philosophers don't help. Okay, they can't think their way out of this problem. One of the things that's happened in the last century is it's become increasingly nihilist. And I've got my philosophy buddies at the University of Florida say that they're weary of the dispute about defining definitions, and they're weary of this other thing. And so this is a problem. So what a lot of philosophers did, of course, became what we call bird watchers. Right? So this is Thomas Kuhn, who wrote a very nice book called The Structure of Scientific Revolution, one chapter of which was a plea for a role for history in the philosophy of science. And what Kuhn basically is saying is, okay, I can't think my way out of this box, so everything I come up with is nihilistic and paralyzing. But no, there are these scientists who seem to be producing, by whatever the scientific method is, whatever they're doing, They seem to be producing something that behaves like it should behave if it were knowledge. Among other things, it confers power. So you can blow up the world with atomic bombs using physics. That means that physics is producing what you would expect knowledge to behave like, because you would expect knowledge to, if you had enough of it, allow you to blow up the world, right? So why don't we go over and look at what scientists are doing and see if we can't figure this out. Now we can do this. This is actually Stanley Miller. It's 1953, a remarkable year in the history of molecular biology. This is the year in which Watson and Crick came up with the structure of the double helix. It's the year that Fred Sanger first determined the sequence of amino acids strung together in the protein. In that particular case, it was insulin. It's also the year in which Stanley Miller took methane, ammonia, water, and hydrogen gases. He put them in a little thing, a little glass bottle with a little reflux condenser, and he sparked electricity simulating lightning. This was supposed to simulate the primitive Earth atmosphere, and what he did when he put lightning through what he assumed was a primitive Earth atmosphere, he got out amino acids. A lot of organic molecules, but the amino acids were the most important things that he got out. They were the key components of proteins. And now this is a long tradition in organic chemistry going back to the early 1800s, where people synthesized from inorganic material urea, a biological molecule, and this was one of the observations done by chemistry to dispel the notion that there was something fundamentally different about animate living matter and inanimate non-living matter. But to be able to say that you get amino acids, clearly biological molecules, out of something that looked like primitive early Earth was quite a shock. And Stanley was quite, Stanley Miller just passed away earlier this year. Now, this turns out to be controversial, okay, because one of the problems we have in educating students is whether we teach them about the Stanley Miller experiment. The state legislature of Texas has a law which forbids the teaching of hypothesis as fact. It's an unarguable law. I mean, you can't argue that. I mean, you should not teach hypothesis as fact. But of course, one of the problems is that Stanley Miller's hypothesis that the early atmosphere had these gases. If you're having any degree of curiosity whatsoever, when I put up on the slide and I tell you, I mean, unless I have impressed you as an authority figure, which I'm not allowed to do as a scientist, but if I tell you that the early atmosphere on Earth 4 billion years ago had methane in it, you're supposed to ask me, how in God's name could you possibly know that? Well, the answer is we don't know that. And further, it's probably not true. And so one of our understanding of what was in the early atmosphere has dramatically changed as we have looked at planets. So you go to Venus, for example, and you see outgassing of carbon dioxide from rocks. There's actually a great way of storing carbon dioxide in rocks. Limestone is a way of storing carbon dioxide in rocks. But there's no good way of storing methane in rocks. And so the argument is when the planets are being formed, we can have outgassing of CO2, not so much methane, certainly not much hydrogen. And so the idea is that this does not lend itself to an early Earth atmosphere. But of course, this is a hypothesis as well. The hypothesis now is that there had more carbon dioxide, CO2, and others. And it turns out that Stanley Miller's experiment doesn't work when the atmosphere is CO2. So when you're teaching students, of course, at high school, the question is, should we teach them the Stanley Miller experiment? You can't say, by the way, that's because it's the culture, right? Stanley Miller founded the field of prebiotic chemistry, which is the field where people try to guess what the early atmospheres were, or the early rocks were, or the early oceans were, maybe drawing on information from the planetary exploration, and then try to get organic molecules out of it. Because the minute you say it's part of your cultural heritage, of course, Genesis is also part of your cultural heritage, and that would be taught as well. So, the other real problem with, this, what's the fact? So all these philosophers that have gone into science and are doing bird watching now all of a sudden come across all sorts of problems. Let me just show you one of them. So is it a fact that life emerged on Earth 3.8 billion years ago? Well, give or take a billion, probably. But, there's Charles Darwin, and there's Lord Kelvin, and of course one of the questions is, who are you going to trust more? This guy or that guy? And what Kelvin pointed out is that if life on Earth emerged 3.8 billion years ago, then the sun must be at least 3.8 billion years old, because what's life without a sun? And then Calvin pointed out that he knows physics and he knows thermodynamics. And so let's assume that the sun is made of the best quality coal that they knew at the time. And of course, you had to have something to burn the coal with. We know the mass of the sun. We know the rate at which the sun is putting out energy per unit time. The sun can't be more than a few million years old. And so, since we all agree, especially the physicists agree, that physics trumps biology, and certainly physics trumps paleontology, right? Here you have a disproof of evolution on first physical principles, and there's nothing more sacred than the second law of thermodynamics to these people, right? And so, nevertheless, you observe that biologists continued to believe evolution even though it had been disproven. Now, that's not good for scientific method. What do you teach a middle school science kid when the scientists are beginning to believe things that are transparently false, based on a hard science, not to be confused with a soft science? Well, of course, now we know the answer is that we know about nuclear fusion. Okay, so the real problem is that the sun is not high-grade coal. It's something else. And of course, but one has to really, in fact, this is part of the scientific method, right? You have to understand that some things you just don't know as strongly as you think you know. One of the ways that you're managing your desire to personally self-deceive, and of course to stomp on your professional colleague, is to recognize that there are some things you don't know well enough, even when you think you know them well enough. And so it's important to let two contradicting ideas go on in time, and in a century or so, they might be resolved, or at least the people who are your scientific adversaries may have died off and left you. That's also called the scientific method. No, I don't think they call you on that side. No, that's okay. So extraterrestrials are more difficult. So there's Francis Drake. Who here has heard of the Drake equation? Raise your hand. So Francis Drake really put this on a napkin and did not expect to have 30 years later this being a fundamental basis for Paul Allen, one of the founders of Microsoft, to invest large amounts of money to search for extraterrestrials signaling us by radio signals. But there it is. There's the equation. Okay. And the number of civilizations in the galaxy able to communicate with us by radio frequency. And so, then, I'm sorry, I made a mistake actually. So N star is the average phase of formation of stars. FP is, this should not be capitalized, is the fraction of stars with planets. N sub B, which is a lowercase n sub B, the equation is the fraction of planets that can support light. F sub L is the fraction that actually develop light. F sub I is the fraction that actually develops intelligence. F sub C is the fraction that produces detectable signals. L is the time that such civilizations send detectable signals. And T sub G is the age of the galaxy. And so you can read in books that my kid has that we can make estimates for all those numbers and come up with a probability of what likely is. So we'll turn on our radio this evening and hear Jodie Foster's contact people for their signals. Right. The only thing that would have made that more persuasive is that he had been wearing a lab coat. So even here we don't have good observation. So what do we try to do up in Ventura as we're throwing ashtrays at each other? Well, the first thing you have to understand is there's a paradox in organic chemistry. There's Stanley actually reprising his original experiment, and you're actually looking at what he actually produces. And what you can do in chemistry, I'm not sure if any of you have run paper chromatograms or separated inks or dyes by running them up a piece of filler paper or done more sophisticated separation, but you can separate that goo, and it is goo, into components, of which that's the goo. We call it tar as a professional term. This is what organic chemicals do when they are sparked with electricity. Now, it's not perhaps unfamiliar in your daily experience. If you take organic molecules and you put them in the oven and you leave the oven on too long, they do not spontaneously generate life. What they do is generate something that is more appropriate for paving roads. Right? The idea of energy plus organic molecules in some excess gives you tar. environment is that what you generate is gunk. And it's worse than that. This is gunk after an hour. If we continue to spark it, or God help us if we heated it, it would get more and more gunk. This is some of the interesting stuff over here, which would be amino acids and sugars and things like that. And so what's quite clear is that organic molecules, if left alone, do this. But on Earth, given liquid order, and if you have the opportunity to exploit Darwinian evolution, and if you can have what we call a chemical disequilibrium, which means to the layman just a source of energy, but not too much, this is what you get. And that's the fundamental paradox. And so what ends up happening is that Darwinian processes become very much a part of the definition of life, not because we have any good theory to say that's the only way that you can get life, but because that's the way it appears that we got the life that we know. And what you'll discover is that all definitions end up being captured by your concept of what is possible and what is not possible. So who here is a fan of Star Trek? Raise your hand. So, I mean, if you know Q, for example, he's not a chemical system. He presumably didn't Darwinianly evolve. He's an intelligent life form. For those of you who are not fans, who is flitting in and out of the continuum and bedeviling the crew of the Starship Enterprise. Now, he did not arise by Darwinian evolution, but if we were to encounter him, we would certainly change our definition of life, right? And so the reason why we don't have a Q incorporated in our definition of life is because we don't think he's possible. That's the way it is. Now, we can change our mind later. But what many of us have settled on as a definition of life is a self-sustaining chemical system that's capable of Darwinian evolution. And so now you've got a problem. Because now, if you say Darwinian evolution is a requirement for life, and of course, if you're going to search for life in the cosmos, you send a probe to Mars, you're going to go looking for chemical systems that might support Darwinian evolution. You've been circular, right? You've actually been, I guess the word would be terracentric. You are looking at the world based on the life that you know here on Earth. You go to Mars looking for that kind of life as well. One thing that's quite clear is that you're going to miss the chance of making a discovery that would inform you that your definition is wrong. And so it's quite useful, right, to remember that, hey, we're scientists as human beings. We're trying to come up with some sort of a concept for universal life. The very first thing we do is to constrain that definition to the life that we know. And, of course, perforce, we will constrain the way we look for life to that life. And so we're not terribly likely to find alternative forms of life unless we do a scientific method, which is a way of controlling our desire to believe what we already believe. Now, I put this slide up because it sort of shows what people are trying to do right now to try to understand the essence of life a little bit beyond what we actually know. And, of course, we always start with what we know. And that's the green quadrant down here at the bottom, which is an evolutionary tree showing the relationships between bacteria, which you know. Eukarya is you, but on this tree, you are like there, and like over here would be corn. So this is a very big tree, and of course the animal life forms that you know are clustered. And that's a very small part of the tree. There's a whole third class of bacteria, which have been called, I think incorrectly, archaeobacteria, because the people who named them thought that they looked kind of old, but that's again a human perception, and not a reality. So, but it's possible, okay, to study this essential process, Darwinian evolution, by looking at the life that we have around us and trying to extract some general understanding of how Darwinian evolution works. Now, if you think that Darwinian evolution is a requirement for life, this makes some sense. One of the things I'll just mention briefly as to how to do this, you can go to travel backwards in time. Now, I'm not going to travel backwards in time in the machine because we believe that that's impossible. What you can do is do something that people do, for example, in historical linguistics. So here I've just put up on, who here is a historical linguist? Raise your hand. Okay, the population is a little low tonight. Historical linguists are well known for not liking rainy and stormy weather. So there are a number of Indo-European languages, and one not. I didn't have to tell you this was Chinese, but have you guessed which one is not an Indo-European language? It's actually transparently obvious with this slide. They can count from 1 to 5 and further, of course. And in German, 1, 2, 3, 4, 5 looks a lot like 1, 2, 3, 4, 5. And in fact, the similarities in the language of German German and English are so great that you cannot deny that those languages are related by common ancestry. But that's even true even if you go over to the Slavic languages. So peti and pente and quinque, these are words that are actually related by common ancestry, as well as indeed the Sanskrit word for five, that is kanka. And so what historical linguists began to discover in the 1800s primarily was, hey, we could actually not only put an evolutionary tree relating to languages, but we could actually infer the sequences of ancient languages from the structures of the descendant languages. And that's important here. We're going to go back in time doing this, but what the historical linguistic does to go back in time is to notice that the German word for snow is Schnee, the English word for snow is snow, and so on. The Romance languages, they decided that S and N were two consonants put together that were hard to say, so SN is lost in the entire lineage leading to modern Romance languages. But the French word for snow, neige, is a homologue of the German or English word. But so is Schneg, the Russian, or the Celtic word Schnektu. And what the historical linguists recognized was that by looking at the strings of letters and noticing the similarities among related languages, not only could you infer that they were related, but you could infer what the sequence of the letters in the word was in the ancestral language, that is the Proto-Indo-European language, we lived more than 5,000 years ago. And so if you happen to meet an Indo-European on the street and you want to make reference to the snow and Big Bear, the word would be something like that. And there, of course, are long PhD dissertations in historical linguistics how you should say that. And that's not important because you're not going to meet an Indo-European on the street. But what is important is by knowing the language, it lets you know something about Proto-Indo-Europeans. Okay, because they must have lived in a place where it snowed. They had no gold. There's no word for gold. There's no word for silver. There's no word for tax-deductible municipal bonds in the language. But they do have dogs and horses and sheep and cows and pigs. They have grain which they put into vehicles which have wheels. They've invented the wheel. And they can count to 100. Okay, and that not ever having met an Indo-European, right, but just looking at the structures of the descendant languages, you can infer all of that about them. Isn't that wonderful? The same thing now goes for biology, because your proteins are also strings of letters made up of amino acids, the same amino acids that Stanley Miller made by sparking electricity through a maybe not so correctly hypothesized primitive atmosphere. And fortunately, the English alphabet has 26 letters, and your proteins have 20 letters, so we actually can have a one-letter code to describe the amino acids. And so the one-letter T is for threonine, and one-letter S is for serine. And if you don't know what those amino acids are, go look at the labels on the health food store bottles. The next time you're there, you'll see what those are. And so now you have, for example, the enzyme from an ox, which has a protein, which has actually, it goes on for 124 of these letters. I haven't put them all here. I've only given you the first 20 just to make the point. But the blue sequence, the ox sequence, is KET, AAA, KFERQ, and so on. That's the string of amino acids in the ox. In sheep it's different, but not much. It's KES, AAA, KFERQ. And by the way, if you are not a believer in Darwinian evolution, you are a believer in a mischievous God. Because if God set this up, right, He put signals that would deceive you into thinking that those sheep and ox were related by common ancestry, but it was not a transparent signal. It was one that required that you go through the entire development of human civilization to the modern point, right, to suffer through the Reformation and the scientific method and Galileo and the whole bit, because it's only 1953, the same year that Stanley Miller did the experiment, that Fred Sanger, who I've already mentioned, figured out how to determine those letters. And what we do is discover if, in fact, these are not related by ancestry, but in fact a creation of an intelligent being, that intelligent being had quite a wit. Now, what's important is to understand, however, that if the sheep and the ox are now related by common ancestry, and that, of course, for those of you who cannot read the Camel sequence, the camel sequence, is more different from the sheep and the ox than either of these is from each other. The camel sequence is SETAAEKFER2. Right? You can go to a tree that says, okay, that means that the sheep and the ox are more recently diverged than either of them from the camel is. But further, you can make a guess as to what the sequence was of the protein in the organism that was the last common ancestor of sheep and ox. Just like you can infer what the structure for the word snow is in European language. Now, this is not Jurassic Park. We don't go back and dig up a 30-million-year-old fossil and then get a mosquito that did it and do the extract the blood. No, what we do is we look at the sequence and say, well, if it's position 1 is a K in ox and position 1 is a K in sheep, in all likelihood, the ancestor had a K as well. Just like the snow in Russian has an S in the first position, and snow in German has an S in the ancestor. In fact, you can go through and do most of that this way. You can, at position 3, you have a problem. The ox is a T, that's a threonine. The sheep has an S, that's a serine. It's hard to know whether the ancestor was a T, and therefore the threonine went to a serine down this branch, or whether the ancestor was an S, a serine, which was changed to a T down the branch leading to ox. But fortunately, we live in the age of Aquarius. There are lots and lots of DNA sequences and protein sequences available for us. The camel has a T at this position, and so now if you know the ox sequence at position 3 with a threonine, a sheep sequence at position 3 with a serine, but a camel sequence at position 3 with a threonine, you infer that the ancestor also has a threonine. Is that clear? People understand that? There'll be a test afterwards. So what? Well, with the magic of recombinant DNA technology, the magic of biotechnology, if we know the sequence of the protein, we can bring it back to life in the laboratory. And so we can actually resurrect proteins, and this is just one of the ones that we've been looking at. Not important for any of you, the details, unless you actually need to be in biochemistry. This is a protein called elongation factor that's used to make proteins. And it's found all over the kingdoms of life. And we can infer the sequence of that protein going back in time about 3 to 3.5 billion years. Inferring the sequence of an ancient protein 3/4 of the way back to the formation of the planet, the magic of recombinant DNA technology allows us to resurrect it in the lab. Now the question is, what do you do with it in the lab? Well, one great principle of geology. Who's a geologist here? Raise your hands. Right, the present is the key to the past, right? That's what we say. The present is the key to the past. So we happen to know we can take a protein and put it into a test tube and measure how active it is. That's this axis. What temperature it's at. Now, in case you didn't know, you live at 37 degrees centigrade. That's 98.6 Fahrenheit. The E. coli living in your intestine lives at that temperature as well. And guess what? The protein is most active at 37 degrees. This is a Darwinian statement. It's like saying that the T-Rex teeth, T-Rex being a meat eater, have evolved to be optimally suited for eating meat. Sharp, pointy, serrated things. The same thing with proteins. The protein is going to live at 37 degrees centigrade. It's going to evolve to be most active at 37 degrees. You go to a hot spring in Yellowstone and pull out an organism called thermos. This fellow lives at 65 degrees centigrade. You pull out the modern, the present is the key to the past, pull out the modern protein, and it's most active at 65 degrees. So just as we know that if we can reconstruct the word for snow into European, it lived where it snowed, we can now bring back to life 3.5 billion year old proteins from bacteria and ask what temperature are they most active at. And there's a green curve that shows that. We actually aren't sure about what the actual sequence is, so we actually make several of them. I forgot to put that on the slide. But the bottom line is that we now say that the very first bacteria that were living at 65 degrees centigrade. Now, that's a piece of a puzzle, right? It's talking about a hot Earth origin of life, but it's done by looking at the descendant sequences and going backwards in time, just like you do in historical linguistics, to get a little piece of the puzzle about the origin of life. Now, mind you, we're still studying something which we don't observe. There's origin of life is still a science with no subject matter. But at the very least, we have bits and pieces from the stuff that we can observe, And frankly, I'm not sure where that fits into the scientific method Billy showed you on the first slide. What's quite clear here is that because you have an experimental method, right, it could have come out anything else, right? You're not actually walking into this with a hypothesis about what the ancient temperature is. You're trying to figure out what it might have been. So there's, of course, all sorts of ways you can look at this little box here, which is this universe of all possible forms of life. And I'm not going to spend you the hours going, and I don't want to bore you too much. There are other quadrants, however, on that chart. Right? One of the quadrants is not working backwards in time, but rather working forwards in time. There's a great NASA provided this marvelous spectrum of these star-forming nebula. I mean, the Earth is formed from a dust cloud, which was caused to nucleate by a supernova exploding about 50 light years from it. You might ask, how do we possibly know that? You know, there are ways, but one of the ways you know about these dust clouds, you can see stars forming in these things, in this galaxy, even at the present time, and that's one of them. But looking at the kind of light that comes out of these, the microwave spectrum, we can form the organic molecules, where C is carbon, and H is hydrogen, and is nitrogen, and O is oxygen. And these are molecules that are coming together. And so one of the questions you can ask is whether this galactic chemistry can constrain the forms of life that can emerge and maybe even help us get to origins. And so, you know, the atoms are all there. This is one of our problems. And we get the molecules, and that's basically the problem of the tar problem, which I've already mentioned. We can actually get pieces of RNA, ribonucleic acid, DNA, deoxyribonucleic acid, out of these interstellar mixtures. Actually, one of the biggest problems is what we call sugar. The R, ribose, is a sugar. Ribose is named after the Rockefeller Institute of Biochemistry, which is where it was discovered about 80 years ago. It's the backbone of genetic material. And one of the problems with it is it's especially prone to get tar. And this is one of the major reasons why people have had a problem getting origins out of prebiotic chemistry, and which is one of the reasons why people at these conferences throw ashtrays at each other. But, in fact, if you want to see an actual example of the tar, there it is. It's a nice little picture there. That's what it looks like, sort of like you might scrape off the wall of your basement. If you had basements in California, I'm not sure it's true. So, ribose is very unstable under conditions where it's formed, and this is actually Stanley Miller himself, the great Stanley Miller, the man who invented the field, gave up on ribose some time ago because it just falls apart. I mean, he says the results show that the stability of ribose is inadequate, so that it precludes them as prebiotic reagents. And that's a problem. Because if you know modern life, remember this, the bottom of that green tree uses ribose, and you know what's up at the top, right, which is all these compounds that come from interstellar space. And if you can't get one of the building blocks, you have a problem. Well, so what do you do? Well, people try to find ribose replacements. This is a slide not to be read by anybody except the chemist. Just to notice all the compounds that have been named. By the way, I have 3 of these slides. I only put one of them in this talk. People have tried to find something else that works like ribose. They can't find anything. But one of the things you have to remember is that organic chemists tend to work in Pyrex, beakers, test tubes. Not good. Planets, of course, the prebiotic soup was in a rock soup bowl. There's all sorts of places you can go looking for this. For those of you who are geologists, I should put some more gemstones in actually for this talk. You actually can get minerals out of rocks that are actually going to stabilize ribose. And one of those minerals, or the whole class of those minerals, are the minerals that contain the element boron, and in borax and things of this nature. It turns out that ribose is boron is a great species. This is ribose, by the way, up close. There's boron, a B. The carbon, again, is C, and H is hydrogen. And the only reason why we put this here is just to say that boron will capture ribose when it's made out of that tar mixture and keep the thing from going on to tar. That's wonderful, and in fact, you can actually have a great demonstration of this, which is, of course, that you have no boron, tar. Boron, no tar. No boron, tar. Boron, tar. No boron, no tar, and so on. You get the idea. And so the bottom line is that, what's kind of amusing about this is that this is exactly, Death Valley is in many ways, looks a lot like the surface of Mars, which used to have an ocean. There's the rover now on the surface of Mars, which does not have an ocean now, but you can still see the minerals, including some that contain boron, presumably, that evaporated on the surface of Mars, just like the minerals in Death Valley arose by the evaporation of water containing boron of the Sierra Nevadas. Now, I'm not sure where the scientific method is in here as well, right, where you're being presented with a problem. It's, in fact, a paradoxical problem. You've got to get from interstellar molecules to modern life. There's an intermediate that you don't know how to get in stable form, so you cast about looking for a solution to this problem. Keep in mind that we're sampling this. We did not look at dozens of minerals that are not able to stabilize ribose. Maybe some of them actually destroy ribose. And so the way in which you actually go about trying to solve a particular problem, because you're focused on the solution of that problem, tends to be a way in which you encounter solutions more likely than you encounter the problems of that solution. And so one of the things that we do on the right-hand side is what we'll call synthesis. This is this idea which was mentioned in the introduction of synthetic biology. And it sort of falls into the category, if you're so smart, why aren't you rich? Right? If you really understand life, why don't you just make some of it? Right? And that is the ultimate test of understanding. I'm not sure where that fits in the scientific method as well, but one thing that's quite clear is that if I try to create new forms of life by a synthetic approach, it solves a problem in the scientific method. So what synthesis does is sets forward a put a man on the moon goal. Synthesize life. Put a man on the moon. I mean, big goals, right? But it's more important as a method or a recipe for discovery because it drives the scientists kicking and screaming across uncharted ground where they are forced to encounter and solve unscripted problems. Anybody can solve the problem as to what's the weight of this soda can, right? It's the unscripted problems that force you to think. More important, if the theory is inadequate, and we ignore the facts to protect the theory, which is what we normally do, because our tenure decision and our grant depends on it, right? The rocket crashes. So we cannot avoid the consequence of our indolence or our self-pity, right? Now, by the way, I put up here something which is a bit embarrassing to NASA. This is the Mars Climate Surveyor. I don't know if anybody has seen any data coming back from the Mars Climate Surveyor. Well, there is none. Well, why? Because Jet Propulsion Lab did the guidance software in the metric system, but Lockheed Martin Marietta made the guidance hardware in the English system. And so what happened was they launched the rocket, and by the way, all the way out, they knew something was wrong. Okay, you read the logs, right? Things are wrong. The rockets, they're burning too much. This is an embodied problem. The physics doesn't provide an analytical solution. You don't actually know where the rocket is going precisely because you got too many Jupiters inside of it, tugging in too many ways. So what you do is you follow, you make mid-course burns to correct where you want to be. And you're making far too many of them. You look at the engineers down below, there's a problem. The people up top were saying, hey, you guys have proved to us that there's a problem. Okay, so it's classic, typical human behavior, right? We just ignore the problem, but you can't do that when you have put a man on the moon or a rocket around Mars. It crashed, which led to the NASA dictum that I thought it was an ounce of prevention is worth a kilogram of cure, I think is what So synthesis drives discovery in ways that analysis cannot. And that's an important point as well, if you don't understand that. I'll just put something up for the chemists in case they're honest. This is our big fun. This is the Watson Crick base pair. Many of you know about the double helix, and there's this little ladder structure where the uprights or the backbone containing ribose, among other things, but the rungs are base pairs. A pairs with T and G pairs with C. And the reason why that works is by these so-called two rules of complementarity, something big pairs with something small. And then you have these red hydrogens that are pairing with blue oxygens or nitrogens. These are hydrogen bonds that join the two. And if you look closely, you'll notice that U, the uracil or thymine in DNA, has a blue pattern up against a red pattern. C is a red blue pattern up against a blue red pattern as you hold these things together with red and blue match. chemists, synthetic chemists can shuffle around groups and get different patterns of red and blue. And we can actually make a DNA alphabet with 12 letters in it, not just the 4 that you have. And of course, this is a new synthetic genetic information. So none of what's nice about it works. In fact, if you are unfortunate enough to have hepatitis or HIV and you go to the hospital, your viral load will be measured and your patient care will be personalized based on technology that comes out of our lab. Your healthcare provider will pay us a small amount of money in royalties, which will go back into the research, and we'll be thankful, but we prefer to have the money in other ways, I suppose. So there you go. So the bottom line is that the fourth way, so you're going backwards in time, right? Understanding the evolutionary process, Darwinian evolution, that you're trying to say is a critical part of the definition of life, and going forward in time to try to get to the green part, starting in the blue part. None of it's particularly scientific method, but it's exploratory, experimental, and things can go wrong. Of course, where they can really go wrong when you try to construct Darwinian systems by scratch, and that's where the rocket crashes. But I would be remiss if I didn't go to the last part of that, which is exploration. Keep in mind that we don't know what's out there. The whole history of the human interaction with the biosphere from Herodotus to the present time has been one of discovery. So when Herodotus hears about the rhinoceros and thinks it might be a unicorn, discovery. When they invent microscopes and see a whole world of microbiology, discovery. And of course, there's an inventory of planets. Saturn is one, Titan, and moving around Saturn, there's a whole bunch of planetary environments that can constrain the forms that life can take. And I'm not sure, I just put a few pictures up here, I'm not sure what you've seen. I mean, NASA for many years has been talking about following the water. And so the major goal when going to Mars is to find water that contains, among other things, minerals that evaporate from water, one of which is minerals that evaporate from water that contain boron. That would be very nice. But, why water? I mean, there are other solids. And let me just go show you this landscape. This landscape is from the Cassini-Huygens mission that came in to Titan. You would think you were landing in San Francisco, right? There are the Sierra Nevadas, there's San Francisco Bay, some more. But the problem here is that this is at 94 degrees Kelvin, minus 180 centigrade roughly. The oceans that you're looking at are methane, and the rocks that you're looking at are about 15 centimeters across. So you're looking at one that we landed on and cracked. That's the first Titan that we have killed. And Mars. Now, by the way, we don't believe it's life, but why? What again makes us so sure of that? What are the primary data? Well, of course, we don't have that. I'm not sure if the scientific method will guess there. Well, I mean, there's all sorts of fun solvents. If you don't want to use methane, there's liquid nitrogen. Let's not go there at this point, at this late hour. So the bottom line is that we've got the scientific method. And I think actually the most important part of it was what I've emphasized in this talk. It's not necessarily the recipe of neutral observation, because there isn't a neutral observation. It's not coming up with an open-minded hypothesis, because we're not open-minded particularly. It's not being persuaded when we don't want to be persuaded. That's near impossible. Or for that matter, not being persuaded by data that contradict our theory. We don't want to be persuaded in the opposite direction. But what it really is a tool, a process that manages human desire to believe what we want to believe. And so when you engage in real science as opposed to sort of the high school or junior high caricature of science, you can see the ways in which people actually try to solve these problems when they try to deal with subjects or sciences for which we don't have the subject matter. Well, with that, let me stop. I'll thank you for your attention. The hour is up. I'm not sure you want to go back outside, but I'll stay here as long as